Hi budding engineers, welcome to Structural Engineering Lectures and welcome to a new place on the design of steel structures. In today's class we shall see the design of laced column in single lacing system wherein the sections are back to back like this, right? This is a design of a built up column, two channels back to back connected by means of a single lacing system, right? In the previous class we have seen the design of compression member as a strut, design of double angle strut. A few problems we have seen. They were connected on one side of a gusset plate as well as on two sides of a gusset plate like this, right? I hope you are enjoying the discussions on our YouTube channel. If you are really enjoying the discussions, don't forget to click like, comment, share and subscribe to our YouTube channel, right? Now before we go to the actual discussion, let us see the brief profile of mine. That is Dr. Rupesh Kumar. Has obtained my BTech Civil Engineering from Nagarjuna University in 1994, MTech Structural Engineering from JNTU Hyderabad in 2000, PhD Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as a professor in Department of Civil Engineering, University College of Engineering, Osmania University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching, research at graduate and postgraduate levels. My research areas include reinforced cement concrete designs, steel structural designs, structural analysis, fault element analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 research papers in international as well as national journals and conferences, organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 2 books, supervising 14 PhD scholars and supervised 30 ME theses. I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks as of now and 150 plus designs of the reinforced cement concrete, steel, composite, low-rise, high-rise, multi-storied buildings as well as road and rail bridges, right? Now before we go to the actual discussion, student, now let us see how we'll encounter these type of problems in real practice, right? This is how built-up column, right? Wherein now we are seeing that this is a single lacing system connected with of 2 bolts here, right? And this is the Batten system, right? This is what a double lacing system, right? A double lacing system along with a batten, or let us also say, right? This is how a single lacing, non-intersecting type. These are the types, right? Non-intersecting type, whereas this is a double lacing, non-intersecting type. This is a battened column. Right? This is how the types of the laced and battened columns. This is single lacing system with non-intersecting type connections, right? Along with the cross members, and this is the double lacing system with non-intersecting type connections, right? And this is a single lacing system with cross members, right? Now we are going to design this problem wherein 2 channels are back to back, which are right. These are back to back, which are provided by means of intersecting single lacing system, right? And even we do have the problems of battened columns like this. This problem we will see in the next class, but however, even in today's class we shall see the design of the batten at the end, at the top as well as at the bottom, right? Now this is all the different systems we'll be discussing today. Now before we start the actual discussions, right, let us see what we are going to discuss. We'll be discussing in today's class the laced columns, right? Now I'll move to the Codal specification at a quicker pace, right? These are the laced columns in general, right? The members comprising of 2 main components, laced and tied, should, wherever practicable, have a radius of gyration about the axis perpendicular to the plane of the lacing, not less than the radius of gyration about the axis parallel to the plane of the lacing, right? Now and a second point is, as far as practicable, the lacing system shall have shall be of uniform throughout the length of the column, right? And um, also the main components shall not be combined with cross members ties perpendicular to the longitudinal axis as shown in the figure 10c that we'll see, right? However, they can be like 10a single laced columns as well as the double lacing column 10b. They are acceptable, but 10c is not acceptable unless all the forces resulting from the deformations of the strut members are calculated and provided in the design of the lacing and its fastenings or connections, right? The next codal specification is the single laced systems on opposite face of the components being laced together shall preferably be in the same direction, so that one is the shadow of the other instead of being mutually opposite in the direction, right? Now, the effective length, the effective slenderness ratio KL by R E effective, right, of laced column shall be taken as 1.05 times the KL by R O, the actual maximum slenderness ratio, in order to account for the shear deformation, right? Means we need to increase by 5% more, right? These are two channels back to back is shown in this schematic, right? Like this, two channels back to back, right? Two channels back to back, wherein they are now connected by means of the lacings like this, right? The lacings, right? Now let us see. Code says that 10A, 10B are suggestible, right? This is how in plan. This dotted line indicates the lacing. Therefore, it is now seen as a Indian standard flat, right? Connected to the channels like this, right? Connected to channels like this, right? Therefore, that is how the arrangement of this lacing system, wherein now we do have this is preferred lacing arrangement, student. Just now code has given single lacing system. This is what single lacing non-intersecting type, right? And this is acceptable. This second figure, code says that it should be the ghost form. Even if I see from AA and if I see from section from BB, it should be the ghost form. Therefore, this is how it is preferred. This 10A is preferred. Whereas for double lacing, right? For double lacing, it is in the form of crisscross like this, right? Just crisscross, right? This is how the double lacing. This is how the double lacing, right? Whereas this is single lacing. Whereas this is double lacing. However, this is also preferred. But what the code says is that this 10C, figure 10C, double laced and single laced systems combined with cross members. Cross members means battened members like this, right? They are not advisable. Until unless you calculate all the forces and prove that these are resisting these forces, right? Then only these are acceptable. Otherwise, not, right? Now, let us see the other codal specification. The width of this lacing flats or lacing members shall be the minimum width of this lacing bars shall be 3 times the nominal diameter of the bolt or that of the rivet, right? Now, and also the thickness of this lacing bar shall not be less than 1/40th of its effective length for single lacing and 1/60th of the effective length for double lacing, right? That is the thickness of this lacing bar, student. And angle of inclination, right? The this angle of inclination shall not be less than 40 degrees and shall not be more than 70 degrees with the axis of the built-up column, right? With the axis of the built-up column. Generally, that axis of the built-up column is vertical axis. Therefore, with that vertical axis, this inclination should not be less than 40. Should not be with respect to this vertical. It should not be less than 40 degrees and should not be more than 70 degrees. But preferably, it should be 45 degrees. And next, regarding the spacing, the maximum spacing of these lacing bars, wherever connected by bolting, riveting, welding, etc., right, shall be such that the maximum slenderness ratio of the components of the main member A1 by R1 between the consecutive lacing connections is not greater than 50, or the second criteria is 0.7 times the most unfavorable slenderness ratio of the member as a whole, whichever is least. whichever is less out of these two, where A1 is unsupported length of the individual member between the lacing points, and R1 is the minimum radius of gyration of the individual member being laced together, right? And next, coming to the top, how these lacings should be designed, right? The lacing shall be proportionate to resist a total transverse shear Vt at any given point in the member equal to 2.5% of axial load in the member, and shall be divided equally among all the transverse lacing systems in parallel planes. That we'll see during the problem, right? And also the slenderness ratio KL by R of the lacing flats, these lacing flats shall not exceed 145. However, in riveted or bolted constructions, the effective length of the lacing bars shall be taken as the length between the inner ends of the fasteners of the bars for single lacing, and 0.7 times this length for double lacing effectively connected at the intersection. However, in the case of the welded connections or welded constructions, it shall be taken as the effective length shall be taken as 0.7 times the distance between the inner ends of the welds, right? Now, that is regarding that of the effective length, student, and also that of the end type plates shall be in accordance with class 7.7. That is what it is back referring to the battened columns, Now let us see also those battened columns, because at the end of this lacing system we will also be designing a battening plate also, like I said. Therefore, the compression members composed of two components, a batten should preferably have individual members of the same cross section and symmetrically disposed about their major axis. However, they should have a radius of gyration about the an axis perpendicular to the plane of the batten shall not be less than the radius of the gyration about axis parallel to the plane of the batten. Now let us see this figure, then you will understand that, right? Now, and also the number of battens shall be such that the member is divided into not less than 3 bays. Now what now I'm showing is 1 bay, like this, right? The entire length is divided into, right, first bay, second bay, third bay means at least 3 bays, means at least 1, 2, 3, 4 number of battens must be there, then only it will divide into 3 bays, right? 3 bays as shown in this figure, right? This is what the center to center distance or spacing of these battens, right? However, the battens are now shown with a dotted line here, right? A dotted line, right? Whereas in the elevation it is seen with a plate or in a standard flat as appropriate, right? We will see that during designs, right? Connected on either side of the column section. The column section may be facing toe to toe, facing each other, or back to back as appropriate. Now, however, for these battened column sections, the effective slenderness ratio KL by R of the battened column shall be taken as 1.1 times the slenderness ratio KL by R, the maximum actual slenderness ratio of the column. Whereas for the laced sections, it was 5% more. Now it is 10% more. Please make a note of the student, right? And coming to the design of the battens, means what should the design force, right? It should be designed to carry a bending moment and shear force arising from the transverse shear force V1 equal to 2.5% of the total axial force on the whole compression member at any point in the length of the member, divided equally between the parallel planes of the battens. That we'll see during the design. Now let us see, and what are the other design forces? Now also code says that the batten shall also resist simultaneously a shear force of VB is equal to V1C divided by NS along the column axis, as well as a moment of VTC divided by 2N at each connection, where VT is the transverse shear force as defined above, and C is the distance between the center to center of the battens in the longitudinal direction, like this. And now we are having that in this figure schematic, figure number 11, and also N is the number of parallel planes of the battens in this figure. Now on either side I would have N is equal to 2, therefore this is 1 and this is 2, and S is the minimum transverse distance between the centroids of the rivets or bolts or welding group, right? This is center to center between the CG of the bolts, CG of these bolts, right? If two bolts are there at the center of these two bolt groups, right? The center of the bolt group to center of the bolt group, right? That is how the distance S is measured. And coming to the top, the size. What should be the size of this batten plate, right? Now, code says that here, when plates are used at battens, the end battens and those at the ends where the members is stayed in its length shall have an effective depth. Longitudinally not less than the perpendicular distance between the centers of the main members. That is what one restriction. However, for intermediate battens, now let us say this is how intermediate batten. However, at the end, if at the end of the column I will be having the end battens. These are what intermediate battens, which will be there in the intermediate locations. Which will be there at the intermediate location. If a batten is there at the end, at the starting of the column, at end of the column, they are what called end battens, right? However, now code says that now for intermediate battens, the intermediate batten shall have an effective depth not less than 3/4 of this distance, right? This center distance, right, between the centers of the main members, 3/4 of this distance. But in no case shall the effective depth of any batten be less than twice the width of one member. However, we'll see that width of this one member, like this, right, not less than twice the width of that member in the plane of the batten. However, the effective depth of the batten shall be taken as longitudinal distance between the outermost bolts, rivets, or welds. Right, the thickness of this batten or the tie plate shall not be less than 1/50th of the distance between the innermost connecting lines of the rivets or bolts perpendicular to the main member. That we'll see during the design tutorial. Then you'll understand, right? Now, coming to the top, the spacing of these battens. In this figure schematic, it is shown as a C, notated by letter C, right? Therefore, how it should be obtained, right? Now, code says that the spacing of the battens and right center to center of its end fastening shall be such that slenderness ratio KL by R of any component over that distance shall be neither greater than 51 or 2.7 times the slenderness ratio of the member as a whole about ZZ axis, whereas for the laced column it is 40 and 0.7 times, right? Here it is 50 and 0.7 times the slenderness ratio, right? Now, coming to the top, the other Codal specification, compression member is composed of two components back to back, right? Here, the compression member is composed of two angles, channels, or T's back to back shall be connected in such a fashion so that the ratio of most unfavorable slenderness ratio of each member between the intermediate connections is not greater than 40 or 0.6 times the most unfavorable ratio of the slenderness of the strut as a whole, whichever is less, right? That is how, if at all two components are back to back, two components, maybe two channels or two angles or two T's back to back, right? In no case the ends of the strut be connected with less than 2 number of bolts or rivets, right? Not less than 2 number of rivets or bolts as appropriate, right? Now, also, in no case the rivets or the bolts shall be less than 16 mm diameter for members up to and including 10 mm thick, and 20 mm for members up to and including 16 mm thick, and 22 mm diameter for members over 16 mm thick. That is how the diameter for each of the thickness. Each of these thickness are specified. Now, this is how the different Codal specifications pertaining to that of the laced as well as a battened column joint. Now, once we see these at a quicker pace, now let us revisit these. Right, this is how just now we have seen that I'm just giving this in the form of nutshell, right? Moment of inertia I should not be less than IZZ, right? B should be at least 3 times the diameter, and thickness of this laced column should not be less than 1/40th times the that center distance between the main members for single lacing, as well as should not be less than 1/60th of that length for the double lacing, and the angle of inclination should be greater than 40 and should be less than 70 degrees, right? should be, and the slenderness ratio should be such that lambda is equal to a1 by r1 should not be greater than zero point 0.7 times most unfavorable slenderness ratio of the entire section as a whole, or 50, whichever is minimum. However, also the slenderness ratio of this laced column should not be more than 145, right? And once we also the slenderness ratio for which we shall design the main member should be 5% more than that of the original slenderness ratio. This is of the different codal specifications in nutshell student. Now let us see. I hope you understood the codal provisions of the laced built-up columns. Now let us see a numeric problem at a quicker pace, student. Right? Now we'll do one numeric problem. Design a built-up column, built-up compression member column 10 meter long, carrying 1080 kilonewtons. 1080 kilonewton. The column is restrained in position, not in direction, at both the ends. Provide single lacing system in bolted connection. Use bolted connections. Use Fe410 grade steel and use F 4.6 grade bolts. Provide two channels placed back to back. Two channels placed back to back. Right now, however, let us see the given data, student. Right? What is the given data? Is both ends are hinged. Both ends are hinged. Therefore, if I go to this table 11, page number 45 of IS 800, student. Now let me go to that page number. This page wherein I do have this page number 45 from IS 800, 45. Yes, 45. I'm there in the page number 45, table 11, right? Both ends are hinged. Therefore, now I do have the effective length as 1. The effective length as 1. Right? Now, this is how both ends are restrained, right? Restrained free, right? At one end as well as at the other end. Therefore, the effective length is equal to 1. Effective length factor is equal to 1. I'm just recalling that and I'm substituting here. Therefore, K is equal to 1. And also keeping in view the load. However, the load is roughly 1100 kilonewton or 110 tons. Therefore, because it is a moderate load, therefore I'm assuming a medium slenderness ratio. Lambda is equal to 70. Right? Lambda is equal to 70. However, if I go to this table 10, page number 44. Let me go to this page number 44, students, from IS 800, page number 44. Yes, from this page number 44. Now we can see that this channel section as well as that of the lacing flat system are that of the channel system, right? Channel section as well as this lacing system are that of a flat, Indian standard flat, right, or a plate. For all these about any axis, the buckling class is C. The buckling class is C, right? Therefore, now I have noted down that property also from IS 800 student. And once I say this is the buckling class C, now I'll go to table 9C, right? Let me go to that table 9C. Just wait for a moment, student. Right? Now I'll go to table 9C, wherein I will have the slenderness ratio for this slenderness ratio of 70. For this slenderness ratio of 70, I will have a this is from page number 42, student, right? 42, right? Therefore, this is table 9C. For lambda is equal to slenderness ratio is equal to 70. For Fy is equal to 250. For 250, the permissible or design compressive stress is equal to 152. Therefore, I'm just making note of that. Therefore, this is how permissible or design compressive stress is equal to 152, and length of the compression member is already given in the problem as 10 meters. Therefore, now what I'll do, the very first heading, as I'll propose the section the proposed section. Therefore, the trial section, right? Therefore, what is the area of the trial section? It is equal to area is equal to the factored load PU divided by permissible compressive stress FCD. Therefore, 1080 multiplied by 10 power 3 divided by 152. It works out say 7105 mm square or approximately 7200 mm square. However, you increase this area by 25 to 50%, so that the section will not fail. However, I want to optimize the section, therefore I'll just I'll increase the area by 25%. Therefore 1.25 multiplied by 7105, it is approximately 8882 mm square, or say around 9000 mm square. Therefore, because we are using two channels back to back like this, right? Two channels back to back, therefore what is the area of each channel is equal to 9000 divided by say 2 is approximately 4500 exactly, or it is 4441 approximately, right? Or say 4500 mm square. However, now I'll go to this SP61 1964 table 2 page number 6, right, from which I'm choosing this is page number 2, student, not this one, right? Now let me go to this page number 2. Yes, I'm there now in page number 2. Yes, this is how from this page number 2 I'm choosing a section. Yes, this is how from this page number 2 I'm choosing a section, a section ISMC 300 at the rate of 351.2 ISMC 300. Let me see this, right? ISMC 300 in page number 6, right? Yes, ISMC 300, student, right? This is at the rate of 35.8 kg per meter, which is having this much of area of 45.64 centimeters square and depth and other properties. Therefore, I'll just note down all these relevant properties from this row. Therefore, that is how noted down all the relevant properties. Therefore, area is equal to 4564 mm square. However, it is just greater than 4500. Therefore, it should be okay. And the radius of gyration about the major axis is equal to 111.1 mm, whereas for such single channel section, radius of gyration about minor axis is equal to 26.1, and CYY is equal to 23.6 mm, and breadth of this plane is equal to 90 mm, and the G, right, is equal to 50 mm, and the moment of inertia over the major axis is equal to 6362.6 10 to the power 4 mm to the power 4, and about minor axis is IYY is equal to 310.8 10 to the power 4 mm to the power 4, right? Therefore, the total area, once I note down these relevant sectional properties from this SP61 Structural Engineers Handbook 1, then what is the total area provided? A pro is equal to 2 multiplied by individual area 4564. Therefore, it works out as 9128 mm square, which is much greater than the required value. What we are trying is approximately 9000. Our exact value is 8882 mm square. It should be okay primarily. Therefore, that is how my trial section. This is my trial section ISMC 300. Two sections back to back. Just now we have seen this Codal specification. Therefore, once we fix the trial section, student, now let us do the next. How much load it can carry, right? Just we have put a trial section, whether it can carry the applied the required load or not. Then only we will further proceed with the designs of the lacing. Therefore, next heading is check for the adequacy of the section. Now, whereas in such case, code says that the slenderness ratio should be taken as, for the laced sections, it should be taken as 5% more, right? Therefore, 1.05 multiplied by L by R min. However, L is equal to 10 meters. However, R min is, you please see that the about major axis, the radius of gyration is equal to 118.1 student, whereas about minor axis, the radius of gyration is equal to 26.1 for individual section, whereas For the built-up section, now the code says that the IYY should not be less than IZZ. That means RYY for the built-up section should not be less than RZZ of the built-up section. Therefore, in such case, RZZ for the built-up section itself is minimum, because this is symmetric about the x-axis. Therefore, RZZ RXX will not change. Therefore, R min is equal to 118.1. Therefore, that is how the result is equal to, say, a value 88.9. However, if I go to this table 9 and see page number 42, let me go to that page number 42, student. Right? This is how I have to have the permissible compressive stress for lambda. Slenderness ratio is equal to 80, FCD is equal to 136, and lambda 90. For 90 it is 121. For 80 and 90. Therefore, this is how for 80 it is 136, and for 90 it is 121. I've just noted down that one. Therefore, now I'll do interpolation. Therefore, for 88.9 it is how much? Therefore, that interpolation will give a result of this permissible or design compressive stress as 136 minus 121 divided by 10 multiplied by 8.9. That works out a value 122.65 MPa, Newton per meter square. Therefore, the design compressive load or strength of this built-up section is equal to AE, gross area. Gross area is equal to 4564 multiplied by 2 such individual sections multiplied by permissible compressive stress 122.65. That divided by 10 to the power 3. It works out, say, 1119.5 kilonewton, which is just greater than 1080 kilonewton. Therefore, it is okay. Means this section can carry the applied load of 1080. Therefore, it is okay. Once it is okay, therefore now what I'll do is my assumed trial section itself is okay. Hence, now I'll proceed with the further designs. Right? What should the spacing of this lacing? Right? What should the spacing of these members? What should the spacing of these members? Right? That now I'll do. Right? What should be this spacing? Therefore, that is the next subheading. Right? Because it is able to carry the load, I'm checking this. Right? Otherwise, another iteration would not have been needed here. Right? Next subheading. The spacing should be such that the code says that the moment of inertia about minor axis IYY should not be less than the moment of inertia about the major axis. That indicates that major previously, which was major axis, that itself will act as if a minor axis, right? For the compound section, right? For there is the two channels placed back to back. For what should be this spacing? What should be this spacing? Now we are finding out this spacing, right? Therefore, let it be SMM, and now how this spacing will be obtained, right? Is using this formula, IYY should not be less than IZZ. Therefore, now I do have IZZ with two individual sections are there, 2 multiplied by IZZ, that of the individual section. Whereas using the parallel axis theorem, the moment of inertia of each of these sections transfer to the CG of the compound section, right? About vertical, this centroidal vertical axis. Therefore, 2 multiplied by IYY of individual section plus area of each channel section multiplied by this S by 2 whole square, because that is a perpendicular distance whole square, right? Therefore, that is how now where only the unknown is the spacing S only, right? However, now as per the code, theta should be greater than 40 degree and should be less than 70 degree. Therefore, now I'm assuming theta inclination of this lacing with axis of the built-up column as 45 degree, like this. Therefore, that is my assumption, right? And we already seen this, right? This is single intersecting lacing system. This is single non-intersecting lacing system. Using schematics also we have seen. And this is double intersecting lacing system, and this is double non-intersecting lacing system. This we already said. However, now I'm trying to do a design of a design of these two channels placed back to back, right, back to back with single, both one intersecting system as well as second one is non-intersecting system. Both of these now we'll do, but however, let us see first two single lacing system with intersecting system, first bit, right? That is the intersecting system, right? Therefore, there is the two channels back to back, and this is that spacing S which we are trying to find out, right? And from steel tables, this distance is given as 50 mm, and the width of the flange is equal to 90 mm. 90 mm, that is also available. Therefore, now from this schematic, now what I'll do is, you please see that at the starting of the columns, we'll put a batten system like this, right? Later on we'll put the lacings like this. We'll put the lacings, right, like this, right? That is how the arrangement. And also there will be a batten at the top of the column like this, even at the top of the column, right? Now, once you understood that, therefore now I'm showing a end batten plate at this end, right? And a single intersecting. You please see that this is intersecting over another like this, right? Intersecting. You please see that both are intersecting here, right? One is intersecting with the other here, right? Whereas this is non-intersecting like this, right? Now, next, I need to find out this spacing using this formula. Therefore, now I'll substitute into this so that what should be the spacing between these two channels which are placed back to back. Therefore, substituting the numeric values, right? Therefore, 2 multiplied by 6362.6 10 to the power 4 about the major axis should be numerically equal to 2 multiplied by about the minor axis moment of inertia is equal to 310.8 10 to the power 4, and the area of each channel is equal to 4564 multiplied by S by 2 plus 23.6, because that is CY, right? This is H square, AH square. Therefore, H is equal to S by 2 plus 23.6 H square. Therefore, solving which, now I'll get a result. S is equal to 183.2, or say is approximately 183.5, or even you can say more also. So that if you say more, then IYY is more than that of the IXX, or even you can say 190 or 200 mm also, no problem, right? Now, once we propose the spacing between the two channels like this, now what we'll do is, now we'll design the lacing system. Now, the main built up section design is over, right? Now I'll go to the design of the lacing system, like this, right? Therefore, now I'll initiate the design of the intersecting lacing system first. Later on, I'll initiate non-intersecting lacing system also, single non-intersecting lacing system, right? Now let A1 be the spacing between the single lacing system as shown in the figure, right? We've already seen that, right? This is how A1, right? Right? And this is how that A1, right? This center of this bolt to the center of this bolt, right, is A1. Therefore, how we'll get this is using this Codal specification, right, where A1 is the unsupported length of the individual members between the lacing points, center distance between the two bolts, right? Because theta is equal to 45 degrees, student. This is how theta is equal to 45 degree. Now I have to have here already the spacing is already available 183.5 plus 2 multiplied by that bolts distance from end of the toe is 50 plus 50, therefore 100. Therefore 100 plus 183.5, it works out say 283.5, right, is the distance of this lacing system from center to center of the bolts system, right, or CG of the bolts, or from center to center of the main members, center to center of the between the two bolts, right? However, now from this schematic, I can say that what is because it is inclined at 45 degree, then what is this length, inclined length of this lacing lacing system, right? Therefore, that from this figure I can find out that cos 45 is equal to 283.5 divided by y. Therefore, y is the length of this lacing is equal to 400.93. Solving which you will get 400.93. And also from figure we can say tan 45 is equal to x divided by 283.5. Therefore, this x is equal to 283.5 mm. These are required during the designs. Therefore, the spacing from this schematic, what is a1? What is a1 is nothing but this length y, right? This length y we have just obtained. Therefore, a1 is nothing but 2 multiplied by this 2 multiplied by y. Therefore, now I'll get this spacing a1 is equal to 2 multiplied by y, or it is a value say 567 is the spacing, right? Spacing. And r1 is equal to ryy, which is a 26.1 for the individual channel section. Minimum radius of variation for the individual channel section is 26.1 mm. Therefore, the slenderness ratio a1 by r1, considering this individual section only, please make a note of this, student, right? As per the code, 567 is just now we obtained that will be 26.1. It works out at 21.72. We should be less than 50. We should be less than 50 as per this IS 800 2007 class 7.6.5.1, page number 50. Let me go to the page number 50, student, right? IS 800, page number 50. Page number 50. Yes, right. This is so that page number 50, right? As per this, just now we have seen that it should be less than 50 for the spacing r 0.7 times the most unfavorable slenderness ratio, right? Most unfavorable slenderness ratio. Therefore, let us also check that one also. Hence, according to this Codal specification, just now we have seen that a1 by r1 should not be more than 50. It is not exceeding. Okay. And what is this 0.7 times most unfavorable slenderness ratio of that of the composite section, right? However, that we already calculated in the previous step for the built up member as say lambda is equal to 88.9. Therefore, 0.7 multiplied by 88.9, it works out as 62.23. Therefore, this uh, value what we obtained 21.72 is less than 50 or 88 or 62.23. Out of these two, 50 is governing. Therefore, 21.72 is less than 50. Therefore, it is okay. However, let us say here you got a value 61.72. You please restrict it to 50. You please make note of this, student. Let us say if you got if you get lambda 1 is equal to 21.72, you restrict it to 50, right? That is how the restriction by the code. And even if I go to this class 7.6.6.1, page number 50, right, from the same page, a transverse shear from the same page is given as 2.5 percentage, 2.5, this one, right? The design of lacing system, right? VT at any given point of in the member, any point in the member equal to at least 2.5 percentage of the axial force in the member shall be divided equally among the transverse lacing systems in the parallel planes, right? Therefore, let us first calculate this result. Therefore, Vt is equal to 2.5 percentage of the load acting on the column, the built up column, 1080. Therefore, it works out at 27 kilonewton. However, we do have two channels taking this much of load. Therefore, we do have two channels. Therefore, capital N is equal to 2. Therefore, 27 divided by 2. Therefore, each of this channel, the load is Vt is equal to 13.5. Vt is equal to 13.5. Therefore, force in each of this channel section is 13.5. Right? This is this 13.5 is acting here. 13.5 is acting. Therefore, and this is already theta, student, right? Therefore, now I can resolve this into the components. Therefore, the force in this lacing system will now work out Vt by n, means 13.5 cosecant theta, right? And the vertical force for the design of these bolts will work out Vt by n, means Vt by n is 13.5 cot theta, right? This is how the design vertical shear force for the design of the bolt Vt by n cot theta, and also the design force in the lacing system is Vt by n cosecant alpha by resolving the components, because this with respect to vertical, this inclination is equal to theta, right? Now let us see then the compression force in the lacing system is equal to C Vt by n cosecant alpha from this figure, right? Therefore, what cosecant alpha is 45 degree, cosecant 45. Therefore, it now works out 19.9. Therefore, this lacing system shall resist 19.09 kilonewton compression load like this, right? Therefore, width of this lacing system B, as per this class 7.6.2 page number 50, right? And as well as the thickness, right? These you already seen in the previous IS college specification, student, right? This is how the width minimum width shall be 3 times the nominal diameter of the bolt, and thickness shall not be less than 1/40th of the effective length for single lacing. Now we are using the single lacing. Therefore, now substituting into this, therefore B shall not be less than 3 multiplied by D. Now let us say, assuming 16 mm diameter ordinary black bolts, therefore 3 multiplied by 16 is 48, or approximately 50 mm is the width of this lacing, as well as the thickness, right? This width is equal to 50 mm. And what should the thickness? The thickness should not be less than 1 by 40th of the length. Just now we have calculated that length as 400.93 from this figure. Length of this length is equal to 400 point, this one, right? 400.93. This y length of this is lacing is 400.93. Therefore, 1 by 40th of this 400.93 will work out approximately 100.2, or say so approximately 10.02, or say 12 mm. Therefore, let the thickness 400, approximately 400 by 40 is approximately 10 mm, or say more thickness 12 mm. Therefore, use 12 mm thick flats. Therefore, now I have fixed the size. Width is 50 and thickness is equal to 12. Therefore, I will be using the Indian standard flat 50. 50 is the width. ISF Indian standard flat. 12 indicates the thickness. That is the designation of Indian standard flat 50 ISF 12. However, now I'll calculate what is the radius of the gyration about the weak axis. R is equal to square root of BT cubed by 12, I divided by A, BT. Therefore, now I have T divided by 12, or say thickness itself is 12 mm. Therefore, it works out root 12, which is equal to 3.46 mm. This is the radius of gyration of this flat about the weak axis, right? And the slenderness ratio of this lacing system, right? L by R. However, the length of this lacing is equal to 400.93 divided by 3.464 mm. It was also say 115.7. However, the code says that it should not be more than 145 as per this class 7.6.6.3, page number 50. Right? Let me just revisit this. Right? It should not be more than 145. This one, right? Should not be more than 145 as per this 7.6.6.3. Right? Therefore, however, the value what you obtain is approximately 115.7 is less than 145. Therefore, it is okay. If it is not okay, student, what we need to do is that first one, either you decrease the length of the lacing system, or increase the thickness of this lacing system, so that the moment of inertia will increase, as well as the radius of gyration will increase, right? If it is not if it is exceeding, let us say I got here 155.7, that is not acceptable. Therefore, either you decrease the length, or increase the thickness of this, or at least you try to restrict this value not more than this 145, to restrict to 145, right? The third option, right? However, here I'm okay. Hence, what I'll do is I'll now go to this page number 44. From page number 44, table 10. We already seen that in the starting discussion itself, this Indian standard flat, because this is Indian standard flat. This is also buckling class C, right? Including that of the channel as well as the angles, right? Therefore, from table 9C, uh, page number 42, let me go to that page number 42, student, right? 42 for lambda is equal to 110 and lambda is equal to 120. Page number 42, right? 42. Yes, I'm there in the page number 42. Therefore, for 110 is 94.6 and 120 it is 83.7. Therefore, now in between, now I'll interpolate. Therefore, for 110 it is 94.6. For lambda is equal to Slenderness ratio 120. FCD, permissible design compressive stress is equal to 83.7. Therefore, upon interpolation, now I'll get for 115.73 it is how much? It is equal to 94.6 minus 94.6 minus 83.7 divided by 10 multiplied by 5.73. Therefore, it works out 88.365. Therefore, the design compressive strength of this lacing is equal to the permissible or design compressive stress 88.365 multiplied by area of this flat system is 50 multiplied by the thickness 12 mm. That will be 10 to the power 3. It works out say 53, approximately 53 kilonewton, which is more than the load coming onto this lacing is 19.09 kilonewton only. However, it is resisting this 50 ISF 12 is resisting 53 kilonewtons approximately. Therefore, our section 50 ISF 12 is the final section as the lacing. Therefore, it is acceptable. Therefore, once we conclude that design for the lacing, let me also check for the tension carrying capacity of this lacing, because under the reversal of the stresses cases, it will, right, if wind is blowing from the this direction, this will be under compression. If wind is blowing from the other direction, it will be under tension. Therefore, whether it can carry the tension force or will it fail in that criteria, that now I'll check. Therefore, now I'll go to this class 6.2, page number 32 of IS 800 2007. Let me go to this page number 32, student, right? At a quicker pace, page number 32. Where is 32? Is 46. Yes, right. Design of tension members. Therefore, T should be less than TD. When design strength due to yielding of gross cross section TDG is equal to AGFI divided by gamma m naught. The second criteria is the design strength due to rupture of the critical section, that are the flats or plates, is equal to TDN is equal to 0.9 AN FU divided by gamma m1. As well as the third criteria. The third criteria is that of the design strength due to block shear criteria, right? Design strength due to block shear criteria, TDB is equal to AVGFI divided by root 3 gamma m naught plus 0.9 ATN FU divided by gamma m1, or TDB is equal to 0.9 AVN FU divided by root 3 gamma m1 plus ATG FI divided by gamma m naught. However, here I'll calculate the tensile strength using the two criteria. I will not calculate using the block shear criteria. For further discussion, you may please see the designs of the tension member designs video, right? Therefore, even this is not carrying that much of heavy load, therefore I will not check for the third check, right? Therefore, let me calculate using these two criteria. The first one, the gross cross section yielding, TDG is equal to FI is equal to 250 divided by 1.1, and gross area is equal to 50 multiplied by 12. That will be 10 to the power 3. It works out say 136.36 kilonewton. Whereas the net section rupture, the critical section rupture, TDN is equal to 0.9 multiplied by AN. Net area is equal to 50. However, I am assuming that I am assuming that 16 mm diameter bolt is to be used. Therefore, from that table, the diameter of the hole should be 2 mm more, 2 mm more like this. Therefore, the diameter of the hole is equal to 16 plus 2, 16 plus 2 from that page number 73. Therefore, the net area or net width is equal to 50 minus 1 reduction of 18 mm diameter hole, net width multiplied by its thickness 12 mm. Therefore, there is a net area multiplied by Fu is equal to 410, that divided by 1.25 divided by 10 to the power 3. It works out say 113.35. Even the third criteria is that of the block shear criteria. However, here block shear will not happen because hardly we are going to provide say not more than 1 volt, or not more than 1 volt. Therefore, block shear criteria will not govern in this case. Will not govern in this case, right? Therefore, TD, the tension capacity or design tensile strength of this lacing system is equal to least of the above two values, right? Therefore, either 136.3 or 113.35. Therefore, 113.35, which is much greater than the tension force under reversal of stresses case also, which is equal to that of the compression force, which is 19.09. Therefore, small tension is 19.09, whereas this itself is resisting 113.35. Therefore, I will not check, because this being very large value, I will not check for the block shear criteria of student, right? Now, therefore, it is okay, even it is carrying the design tension force also. However, once it is okay, then I'll go for the bolted connections, right? Now I'll initiate the bolted connections, right? Uh, that I'll design the intersecting double the intersecting lacing system as well as non-intersecting lacing system. However, in the intersecting lacing system, the shear is in the double shear, right? Like this, the shear is in the double shear because now the bolt has, right, two weak planes with that of the main section as well as that in between the two lacing systems, right? However, for non-intersecting system, it is only under single shear. It is under single shear, right? Therefore, now if I go to this class 10.3.3 from page number 75. Let me go to that page number 75, student, at a quicker pace. Page number 75. Yes, I'm there in page number 75. Yes, this is of the page number 75. The shear capacity of the bolt VDPB is equal to VNSB divided by gamma MB, where VNSB is equal to FU divided by root 3 multiplied by NN multiplied by A and B, as well as the bearing capacity of the bolt from the same page. I have to have VDPB is equal to VNPB divided by gamma MB, where VNPB is the nominal bearing strength of the bolt, which is equal to 2.5 kb dt Fu, where kb is the least of the four results. 1 E by 3d naught, 2 P by 3d naught minus 0.25, 3 FUB divided by FU, 4 is 1. 4 is 1. Therefore, using this now, let me calculate what is that bolt value. What is that bolt value? Therefore, using this first one, I am calculating the design shear strength of the bolt for the intersecting lacing system. For the intersecting lacing system, it is under double shear. Therefore, n is equal to 2. Therefore, n is equal to 2 multiplied by 157 is the net area of these bolts. Net area of the bolts is 157. That multiplied by this Fu is equal to 400. Fu divided by root 3, right? Divided by 1.25 divided by 10 to the power 3, 10 to the power 3. Therefore, it now works out, say, a value 58 kilonewton. 58 kilonewton. Therefore, that is how the design shear stress is equal to 58.01 kilonewton. Whereas, for calculation of kb, what now will do is the first criteria E divided by 3d naught. However, D is equal to 16 mm, therefore D naught is equal to 18. Now I have to have from the first criteria E divided by 3 D naught is equal to 24 divided by 3 multiplied by 18, which is equal to 0.44. The second criteria is P divided by 3 D naught minus 0.25, 40, because P is equal to 2.5 multiplied by D 16. It works out say 40, therefore I am using the same value 40 divided by 3 multiplied by 18 minus 0.25 is equal to 0.49. The third criteria FUB divided by FU 400 divided by 410 is equal to 0.975. The fourth criteria is 1. Therefore, minimum out of this is equal to 0.44. Hence, the design bearing strength of the bolt VDPB is equal to 2.5 multiplied by 0.44 multiplied by D. D is equal to 16 mm. T is the thickness. The minimum thickness is 12 mm now. 12 mm. Therefore, that multiplied by 400 divided by 1.25 divided by 10 to the power 3. It works out as 67.58 kilonewton. Therefore, the bolt value is the least of these two. Therefore, 58.01. 58.01. Therefore, the number of bolts required N is equal to the compression force in the member or that of the tension force is equal to 19.09 divided by each bolt can resist up to 58 kilonewton in double shear. Therefore, now I do have the number of bolts is much less than 1. Therefore, R say 1 number of bolt, right? 1 number of bolt, right? However, um, previously we have designed using intersecting lacing system. Now, if I redesign this, assuming a single non-intersecting lacing system, therefore in such case like this, right? Therefore these are non-intersecting now. Previously they were intersecting one over the other like this, right? One over the other. Previously they were intersecting like this, right? Now this is not intersecting, therefore now the bolts will be there under single shear. Like this, right? Therefore bolts are there only under single shear, right? Only single shear. Therefore, in such a case, now we can find that whereas we already obtained for single shear the strength of the bolt in single shear is equal to 29.05. However, in bearing it worked out a value 67.58. Therefore, the least of these two is 29.05. Hence, the number of bolts that are required for this also is less than 1. Therefore, R say 1 like this, as shown in this figure for non-intersecting lacing system, right? Now, once I do this, now finally I'll design that of the end batten or tie plate. Now that end batten is what called the tie plate. Therefore, IYY should be not less than IZZ. This Codal specification we already said, and at least it should be divided into 4 panels, and the slenderness ratio lambda is equal to 10% more than that of the slenderness ratio, and transverse force VT is equal to 2.5% of the total axial force, and VB is equal to VT C divided by NS. Right? Therefore, all these Codal specifications we have seen, student. Therefore, now what I'll do is now I'll go to this. Sorry. Once we see this Codal specification, now I'll go to this, and also the moment should be Vt C divided by 2n, right? And the size d effective distance should not be less than the perpendicular distance between the centroids of the main members, and effective depth should not be less than 2 times the width of the flange, and the thickness of the batten or that of the tie plate should not be less than 1/50th of the center to center distance for the intermediate battens, and for the intermediate battens it should not be less than 3/4 of this distance, and the spacing should be such that slenderness ratio should not more than 50 or 0.7 times the slenderness ratio of the compound section. And for back-to-back batten systems also we have seen lambda should not be greater than 40 and should not be greater than 0.6 times the slenderness ratio of the composite section, and diameter of the bolts also should not be less than 16 per thickness. 10 mm should not be less than 20 mm per thickness in between 10 to 16 mm, and for diameter 20 for thicknesses more than 16 it should be less than it should be 22 mm. Therefore, that is of the Codal specifications, right? Once we see that the design of end batten, right? end batten, or it is a tie plate now, right? It is a tie plate. Therefore, now I'll fix what should be the size of this end batten, right? As per this codal specification, now it says that as per this class 7.7.2.3, the DE, right, should not be less than the perpendicular distance between the centroids of the main members, right? Let me go to this 7723, student, 7723, page number 51. 7723, page number 51. Just bear for a moment. 51. Yes, 7723, page number 51. As this one size, right, shall have an effective depth longitudinal not less than the perpendicular distance between the centroids, right? Therefore, that is what now I'm calculating here, right? Therefore, D should not be less than this spacing S plus here one cy as well as here another cy. Therefore, it is now upon substitution, D should not be less than S plus 2 cy. Therefore, upon substitution, it works out say 230.7. 230.7. However, this effective depth shall not be less than 2 times the width of the flange. However, the width of the flange is equal to 90 mm. Should not be less than 180. However, this 230.7 is much greater than 180. Therefore, okay. If let us say if you get this result as 130.7, don't accept. It is restricted to 180 mm. Here it is okay. Therefore, once it is okay, therefore the overall depth of the plate, assuming edge distance E is equal to this already told 1.5 times the nominal dia 16 mm or say 27 mm, or I am assuming it to be 30 mm. Therefore, the overall depth of this plate is equal to effective depth 230.7. This what we got plus 2 edge distances 2 multiplied by 30. It works out say 290.7, and the thickness of this batten plate or end-type plate should not be less than 1 by 50th of S plus 2G. Therefore, upon substitution, 1 by 50th of S, 183.5 plus 2 multiplied by 50. It works out say 5.63 or say 6 mm. Therefore, the length of the batten plate is equal to S plus this width of this flange, two widths of the flange. Therefore, it works out say 183.5 plus 2 multiplied by 90, 263.5. That is how the design of the end batten plate is now seen as this length is equal to 363.5 student, right? This length is equal to 363.5, right? This now I'm showing here, right? And the depth is equal to 290.7, and this thickness is equal to 6 mm, and also the end distance of the bolt is 30 mm and 30 mm. However, the total depth itself is 290.7. Therefore, 290.7 minus 60, that divided by 2, it is approximately 120 and 120. Therefore, the pitch of the bolts is equal to 300. Or say instead of say 290.7, I'll say 300 mm. Therefore, I'll use a 300 mm depth plate instead of saying 290.7, right? Not less than actually, right? Therefore, if I use 300 mm depth plate, now two edge distances are deducted, that divided by 2. Therefore, the distance between the center to center of these bolts is equal to 120 mm, right? That is how the design of the end tie plate or that of the batten plate also, student, right? This is how we have seen the design of a built up column like this, right? Finally, the design is looking like this, right? There is a two channels back to back which are provided by means of a single intersecting lacing, right? Just we got only one bolt only, therefore there is how the one bolt, right? That is how they are intersecting one over the other. However, you please see that the channels are back to back, and this is how the batten plate at the top, right? Also a batten plate at the bottom, right? That is not seen in this view, right? That is how the design student, right? That is how the design. I hope you understood the discussions what we had in today's class. Therefore, if you have really understood, don't forget to click like, subscribe, share and comment to our YouTube channel. We'll meet in the next class with another discussion on the design of the battened built up columns or compression members. Till then, bye bye students.